Alright guys, today we're going to start talking about complex factoring, which by the time we get done with it, it's going to be one of the easiest things that you're going to be required to do for the course. But sometimes to make us understand, then we've got to look a whole lot more conceptually. So kind of hang in there with me today. I promise by the time we get to the end where I'm actually showing you how to apply this, it's going to be really, really easy. Okay? So complex factoring is really limited to a singular type of factoring, and that is factoring a sum of squares, okay? Which seems strange because we know we could always go and factor a difference of squares, but how are we supposed to factor a sum of squares? And the answer is you do the same thing, okay? So first, if we go and look back and think what we know about factoring a difference of squares, you already know that you can factor x squared minus y squared. That is the definition of a difference, minus sign, of squares, x squared and y squared. That will always factor into x plus y times x minus y, which you hopefully remember are conjugates of each other. That's why they eliminate that middle term, because they're conjugates, okay? That's what conjugates do. But we haven't been able to factor a sum of squares, because x squared plus y squared, well, we'd either have to do x plus y times x plus y, which is definitely not going to give us x squared plus y squared, or we'd have to factor x minus y times x minus y, because that's the only way that we could get any of that sort of stuff to work, okay? And the hard part is, it doesn't. Because if I use the distributive property and multiplied all this stuff, I'd end up with what? X squared plus xy plus xy, so there's no conjugates here, they're not eliminating each other, and then plus y squared, okay? Or here I'd end up with x squared and then minus xy minus another xy and then plus y squared, but again, these middle terms here, they're not being conjugated, okay? So they're not going away. It's just x squared plus 2xy plus y squared, or x squared minus 2xy plus y squared. So how in the heck am I supposed to factor this positive thing? And that's when things start to get interesting. Okay? We could go through and use certain properties that we've learned about as they pertain to imaginary numbers and what a positive is. So first, we're going to use the fact that we could, if we wanted to, rewrite any plus sign as a double negative, because minus a negative is the same thing as a positive, right? Okay, so in theory, we could go and rewrite this plus sign as a double minus, okay? Writing that with a coefficient, it would look like x squared minus negative 1y squared, okay? Using what we know about the value of the imaginary number I, okay, we know that negative 1 is the same thing as I squared. So could we substitute an I squared in for that negative 1? Absolutely. So we could choose to rewrite x squared plus y squared as being the exact same thing as x squared minus I squared y squared. Because I squared y squared is negative y squared, and minus negative y squared is plus y squared. So we're doing all sorts of crazy stuff right now. It's weird, I know, but it's kind of cool at the same point, okay? And because this rewrites as I squared y squared, we could also express it as yi quantity squared. So what did I do? Using an imaginary number, I literally just turned a sum of squares problem into a difference of squares problem. Math. Woohoo! Okay? I know how to go and do a difference of squares factorization. Okay? So that's what we're going to go and take a look at here. All right? So, if we were to go and show you the mathematical way to go and factor this difference of squares problem, okay? X squared minus I squared y squared, we'd realize that there's a difference because we're subtracting, and we've got two perfect squares, so difference of perfect squares. The square root of x squared is x. The square root of I squared y squared is yi. So using the conjugate to help us write those factors, it's just x plus yi times x minus yi. All right? So I realize this all sounds probably really weird right now, but as soon as we start doing an actual example, you're gonna be like, oh my God, he went through all of that for that? Just freaking tell us how to do it. Jeez. Okay? So I'm gonna look at the first example where we're gonna try and factor x squared plus 25. Because there is a plus sign here, I'm going to recognize this as being a sum of squares. So what does that mean? It means that I'm going to pretend it's a difference of squares first. Okay? So what is the square root of x squared? X. What's the square root of 25? Well, we should know that is 5. So this is going to be x plus 5 and then x minus 5. But because this was in fact a sum of squares, okay, again because of this plus sign right here, it's plus 5i and minus 5i. That's literally it. That's the answer. So yes, you could walk away and say, all right, if it's two perfect squares, if it's a minus sign, just do the numbers, and if it's a plus sign, throw an I on it. Yes, that will get you the answer. Okay, but I wanted to go through all of this explanation so that you could see mathematically why it works. I don't want math to be like weird voodoo stuff where you never know what's going on. You just kind of blindly trust somebody that's telling you stuff. I want to explain it to you. Even if you don't understand it right off the bat, you can see, hopefully, the more problems that you work out, that it does actually work. Okay? Could we go through and check that this works to verify? Sure. Using the distributive property, x times x is x squared. X times negative 5i is negative 5xi. Positive 5i times x is positive 5xi. And positive 5i times negative 5i is negative 25i squared. Okay? So, remembering what we remember about conjugates and imaginary numbers, okay, positive 5i and negative 5i, those are inverses, and they undo each other. What is this I squared going to turn into? A negative 1. What's negative 25 times negative 1? A positive 25. So this is going to simplify to just x squared plus 25. Okay? So it does in fact work. We can also use this if we have problems that are a little bit more than just, leading coefficient of 1 and little baby guys here. So I could look at the second example where we're factoring 4x squared plus 81 and kind of do the same thing. Is there a GCF here? Not really. Can I go and take the square root of the first term, which is 4x squared? Sure. Square root of 4 is 2. The square root of x squared is x, so it's 2x, product property. Remember that from the second day? And then we can also go and take the square root of 81, which is just 9. Okay? So those are the two values that I'm going to be using. Because this is a sum of squares, I know that I'm really going to be dealing with like plus 9i and minus 9i. But this will factor into 2x plus 9i, and then its conjugate, 2x minus 9i. Because 2x times 2x gives you 4x squared. Positive 9i times negative 9i gives you negative 81i squared, which is really positive 81. And because these are conjugates, those middle terms are going to undo each other. Okay? So we should be good to go. Just remember that factoring the sum of squares is almost the same as factoring the difference of squares. All you got to remember is that it's going to involve an imaginary number as well.